So, hello everyone. I'm Manolo, and I'm currently at the Imperial College of London. But I'll present a work I did last year in the Natural History Museum in Paris with Olivier Gasquet. And the things I'm presenting here rely heavily on these two papers. And I'm glad that Hélène did a great presentation on especially this one here. So it will save me a lot of time to explain, for example, the encoding they did for the phylogenies. So this is briefly just for you to remind yourselves. How is it done? So we order the tree, laderize the tree, and then we encode the internal nodes and the tips. Okay, and this is a very compact way of representing the tree, and it also has this feature that once you have this encoding, you can get back to the tree if you want. Okay, so it contains the information of the tree. You can get back to it if you want. And for both of those two papers, they use this encoding or a similar version of it with a convolutional neural network with this architecture here. Okay. And since I think it's the first talk on phylodynamics, I'll briefly introduce you to the models I'm using here. And the simplest model that we can come up with for phylodynamics is this BD model. And it's analogous to the SIR model in epidemiology, the classic model in epidemiology. And this model, it contains three different classes. The red one is the infectious class that can infect new people. The R class is the sample class that are removed upon sampling. And there's also one unsampled class. So how does it work on the phylogeny here? We have the nodes as transmission events. And we have both sampled tips and unsampled tips. Okay, so what we actually have, our phylogeny looks like this. And having those phylogenies, we can estimate some interesting parameters for epidemiology. For example, the infectious period, which is how much time does an infectious individual can infect new individuals. And also the R node, this was very famous parameter during COVID, which is a measure of how the epidemiology is spreading. Another more complex model that can be used here and that I will talk about a little bit is the what's called BDSS, which is a birth death model with super spreaders, so BDSS. And it's exactly as the BD model I showed first, but now the infectious class, this here, we divide it into subclasses. One is infectious S, which are super spreaders, so individuals that spread the disease faster than the normal individuals, and non-super spreader class. And again, we can estimate the infectious period, the reproductive number, and then we have two new parameters. One is for the super spreading transmission ratio, so how much more does a super spreader transmit the disease when compared to a regular spreader, and the super spreading fraction, which is what's the fraction of super spreaders in our total sample. Okay, so these are the results from this first paper on phylodynamics, Voznica 2022, and they performed better. So this is CBLV, the encoding. They perform better than the state of the art, which is BEAST. And this is just for the BDSS model, okay? Because I'll focus more on this one. But interestingly, when they use only summary statistics, they perform better than this encoding. So summary statistics are pretty good at this task as well. So one question that Olivier came up with and asking me to, what are the summary statistics they used? So those 6 classes of summary statistics on the tree topology, the branch lengths, and so on. And those summary statistics were used on a feed-forward neural network, simple architecture, okay? So we ask ourselves, especially Olivier, can we do better than that? Because we're doing worse than summary statistics. And so that's why I joined his group, and I tried to make something a little bit better. So we started with graph neural networks because they make sense, since we have a graph, like a tree is a graph. But we have a lot of problems. We tried some different approach of graph neural networks that uses this diff pool approach, and it worked for population genetics in this Korfman paper. So I was excited about trying it with my phylogenies. And the idea here is just you have the graph, but you pull the nodes locally. So it's not like you're pulling everything together. So it was supposed to work a little bit better for information transmission of information from distinct nodes and distant nodes. But unfortunately, our results were a little bit not very exciting. And the results that Hélène showed us in the first day when they tried the graph neural networks also kind of confirm what I had. So it makes me feel better that I was not doing something too bad. It was not on my side. So yeah, I think they are useful. They can be very useful, the graph neural networks, but we need to work a little bit more on making them work with this type of data. I also tried this recursive neural network approach that was described in this paper. Also didn't get some very exciting results. And so I thought about coming back to what I know would work, and something that I was more familiar with were the CNNs. So I just came back to the CNNs, and my idea was to change the representation a little bit and maybe change the architecture to get something better from them. And this is the representation we came up with after a lot of trials and errors. And the idea is that we take local statistics from each node. So in this example, I'm looking at node N, okay? And we are taking statistics in 3 different hierarchical levels. So in green is what we call no context. So we just have I'll go through all those statistics, but we are looking just for the ancestral node of interest, the root, and the most recent tip, for example. Then we go to a higher level, or one generation context, which is in red. So we're looking to this node and those 2 child nodes as well. And we even went one step further and encoded 2 generation contexts. So then we go to this node here. So the father, the great grandfather of the node, and the grandchilds as well. And we also wanted to see if I'm going to show it later, if it works for diversification. So we added only one extra feature when we are doing diversification with different states of the tips. And is this value here, the N star. And it's just the number of leaps of type 1, since we have 2 types, in the node. The number of leaps that are related to this node that are from type 1. I'll go through that in more detail. So let's take an example on how does it work. So looking at node N again, we have the sampling probability, the distance to the root. So in this case, the root is here. So let's assume that each branch length is 1. So the root is 1, 2, 3. So the value is 3. Distance to A1 is just 1. The age is actually the distance from this node to the most recent tip. So in this case is 1, 2, 3, and so on and so forth. And we also have the number of leaves associated to the node. So this node here is 1, 2, 3, 4 leaves. And so this is how we encode it. And when there is some absent value, we just plugged in -1. So for example, distance to the child 1, 1, when the child 1 is a tip, there is no child 1, 1, so we just plug in -1, okay? So if you are very close to the tips, there will be a lot of -1s here, or if you are a tip, there will be a lot of -1 in this representation. And then what architecture did we use? So this is the architecture we use. It's kind of similar to what was used in those two papers, but we did a few things different. And what we did different was that we separated the leaves and the nodes into different channels. And we did the convolutions separately for the leaves and for the channels. And this is called a depth-wise convolution, when you do the convolutions on the channel separately. And then after that, we do a point-wise convolution. So we just combine the information from the feature maps of the two different channels. And the combination of this is called depth-wise separable convolution, if you want to look how does it work. And then after that is just one more convolution filter, pooling, and a feed-forward neural network. And then an output layer with the parameters. Or if you want to do model classification, it will be a softmax layer. And why did we choose to do these separate channels? There is some reasoning behind it in this paper from Anazukova. And in this paper, they do the likelihood. They were able to calculate the likelihood of this phylodynamic, one of those phylodynamic models. And to do that, they did with this formula that separates the tips and the internal nodes. So the calculations were separate, and they saw that it was important. Also, we need to add the sampling probability when we're doing this. That's why we are adding this information redundantly to all the nodes. And in this case, to be more general for their model, they included the childs. So that's also why we thought about this context, adding this context in our representation. And these are the results, just comparing the three levels of context with BD and the BDSS model for phylodynamics. And we saw that the context helps, in bold is the best approaches, and in underline is the ones that were not the best ones. We saw that context helps just for the most complex model. So here we have everything is bold in BD, you see. But context helps here in the BDSS. When we train with 100,000 trees, it helps a little bit. And with 10,000 trees on the training set, it helps more. So there is some helping on the context. And how about when we compare with the state of the art? And now we just, since in the paper, the previous results I showed you, BEAST was really bad. So we are just comparing to PhyloDeep. And one interesting thing to look is that PhyloDeep was trained on 4 million trees, and we are training on 100,000 or 10,000 trees. Okay. And if we look at the 100,000, those results in red, we got the same accuracy or better accuracy than PhyloDeep either with summary statistics or the CBLV representation in all cases with 100,000 training trees, so way less simulations. And even if you look when we train with 10,000 trees and compare with CBLV, we got similar results in most of the parameters. So I think this is very exciting results, especially when you need to simulate more because the models in PhyloDeep doesn't fit well to your data. So yeah, I think this is pretty exciting. And so we tested this on a real data set, and for the sake of comparison, we decided to use the exact same data set as PhyloDeep, and this HIV data set from Zurich. But one thing of this data set, and those are the results from PhyloDeep, the previous approach. They did some model adequacy. The empirical data fell within the cloud of simulations. But if you look at their priors and their posteriors for some of the parameters, it doesn't seem that the priors are very appropriate, right? So here the upper bound is 10. The upper bound of the estimated values are 12. Here is 10, but they force it to be 10. They force a maximum boundary. And in BEAST, it was 26. So we decided, since we don't need so much simulations, let's simulate under these different priors and see how it goes. And those are the results. In yellow is CBLV. in the gray boxes are the priors that they use. So if, for example, if you look at this parameter here, the posterior distribution is much narrower for CBLV, but the prior is also doesn't seem to be very appropriate for what they are estimating. So when we change the prior here with our approach, both with summary statistics and with the CNN approach, then we see that the distribution of the posterior is very broad. So actually, it seems that this parameter is very hard to estimate, as in the same thing for this parameter. But those results are probably because of the prior that was used. And so we also applied it to classification. We just look at this BIS model, the binary state. So here we have two different states, and speciation and extinction rates relate different speciation and extinction rate related to these two states. And again, this is the encoding that was used in the paper that Ellen showed us in the first day. And it's similar to CBLV, how it works. Those are the results, and they did better than the state of the art. So the best approach was the pink one, CNN CDV. And so how does our approach perform in this case? So when we compare the three different contexts, this is just the new approach that we are proposing. We don't see much of an improvement when we put the context in this case. Just a little bit from the one generation context to the no context, but very slightly, only in this parameter here. And in this case, there is no improvement, and even in this case, it was a little bit worse. So generation doesn't generational context doesn't seem to help much in this case. And when we compare to deep time learning, which was trained on 1 million trees, we got higher accuracy in most of the parameters, even when we train with 10,000 trees. So I think this is also very exciting and opens possibilities to train different models, more complex models, and doesn't need too much simulations. And now for the empirical data, if I have time, yeah. We also use the exact same empirical data set for the sake of comparison. So again, in the paper, they did the model adequacy. So the empirical data falls within the cloud of the simulations. And so in this case, the priors seem more appropriate to the real data set. So we kept the same priors. And those are our results and the results from deep time learning. And it's difficult to assess which approach works better, but we got closer to the maximum likelihood estimate in all cases. So I think it's a good thing. And that's it. I would like to thank Olivier for helping me with this, and all of you for listening.